Good afternoon. My name is Seifu. I am going to present our research work entitled Data-Driven Based Optimal Placement and Performance Analysis of Full Dimensional MIMO for Enhanced 4G Mobile Network under Realistic Deployment Scenario. The presentation outline is arranged in this way: background and motivation, objective, methodology, deployment scenario, result and discussion, finally conclusion and future work. When I start from the first part, demands for data service have been continuously increasing due to the introduction of different data-intensive applications and services. To accommodate this data demand, various technological advancements have been investigated and incorporated in different generations. Expanding operating bands and full-dimensional MIMO are among those technologies. Full-dimensional MIMO is a technology that utilizes 2D antenna arrays that supports 3D beamforming. Although benefit of this technology is researched well, approaches to exploit their benefit in a cost-effective way considering realistic network environment is rarely reported. So, regards to its related works, several research papers have been conducting regarding on the use case of 3D beamforming. However, previous works neglect or rarely address the issue of how and where to use this technology in a cost-effective manner, and also most of them neglect the effect of realistic network environment and they works on legacy operating bands. Hence, this work presents a data-driven antenna planning approach for cost-effective optimal full-dimensional MIMO placement for some 6 GHz operating bands and under realistic network environment. So, based on the gaps, the aim of this paper or this work is to apply a data-driven approach for optimal and cost-effective full-dimensional MIMO placement and to compare the performance impact of the studied configuration with the existing LTE network as a reference configuration under realistic environment, considering sub 6 GHz operating bands. This is the methodology that we followed to come up with the result. First, we started by reviewing related works and then system model and problem formulation, considering again realistic network environment. That implies network topology, propagation model, antenna pattern and user distribution, and then simulation using those tools, the ProMan, AMAN, the Wallman from WinProp and the MATLAB, finally result comparison and justification. With regards to deployment scenario or performance studied area, to study the performance impact of the proposed approach, we selected a site in Addis Ababa, specifically around Bekele, and it is a place where high data traffic is recorded, and it consists of 80 macro sites or 54 3x1 cells or 180 3x2 sectors. With regards to multi-objective problem formulation, in this work we consider a downlink LTE mobile network having an area of A, K number of sites and L number of users. So, before upgrading is applied on the existing site, the USNR performance is given by this equation or this expression in equation given by equation 1. The received power from the serving cell over the sum of interference excluding the the serving cell plus the noise term. When the existing macro cell is upgraded with FD-MIMO having cell splitting capability, the SINR performance is given by either of the two expressions. When the user is associated with the outer sector, the SINR performance is given by the received power from the serving cell over the sum of interference excluding the serving cell plus the noise term. And when users is associated with the inner sector, the SINR performance is given by the received power from the inner sector over the sum of interference plus the noise term, of course again excluding the serving cell. So again the throughput performance is given by the Shannon formula, the bandwidth efficiency times the number of PRP times bandwidth per PRP times the logarithm of 1 plus SINR over SINR efficiency. And when upgrading is applied on the macro cells, the throughput performance is given by the bandwidth efficiency times the number of PRP times bandwidth PRP times the logarithm of 1 plus SINR. After upgrading is applied on the macro cell over the SINR efficiency, and based on equations 3 and 4, the throughput performance gain is given by the throughput after upgrading minus the throughput before upgrading over the throughput performance or the user throughput performance before upgrading. So when m number of macro cells are upgraded out of a total of 3K cells, the aggregate throughput performance is given by equation 6, or the aggregate throughput performance is given by the aggregate user throughput served by the existing macro cell plus the aggregate user throughput served by the upgraded one. So for every m number of macro cell selection, we have p number of options given by equation 7, which is 3k factorial over 3k minus m factorial times m factorial. So equation 7, from equation 7, we can write this question. So the question is how the optimal location are identified among those p options, considering 5 percentile or 10 percentile and average user throughput. So this is a kind of multi-objective optimization problem which can be formulated as minimizing f of x, f1 of x, and minus f2 of x, where f1 and f2 are, or f1 is the number of upgraded cells, and f2 is aggregate throughput, and x is a vector which shows the status of macro cells. So this problem can be solved by evolutionary algorithm, because this algorithm do not require convexity or concavity. According to 36, non-dominated sorted genetic algorithm, or NS to GA, has less computational complexity, fast convergence, good scalability, and empirically very near optimal compared with other compared algorithms. So this algorithm accepts initial population's fitness function and stopping condition as an input, and gives an individual that can give a best fitness value as an output. For our case, the initial population are denoted by X, which can be shown in the figure, where Z is the number of population, XIZ the status of macro cells, and of course we have a total of 3K number of cells. These are simulation parameter and study scenario. For instance, in simulation parameter, the transmit power is about 46 dBm. The UE number or the 1337. The noise figure is 9 dB, the bandwidth efficiency 0.5, the SINR efficiency 0.85. Cell association is based on RSRP or reference signal received power. Scheduling is round robin. And also, regardless to studied scenario, we consider three scenarios. The first scenario is assuming both the inner and the outer beams are upgraded with the same operating bands with 1.8 GHz. In case 2, we assume again the same operating bands but with different frequencies, that's 3.6 GHz. Case 3, upgraded with different operating bars, the 1.8 GHz and 3.6 GHz. When I come to the results and the discussions part, figure 2 and figure 3 are plotted to compare the UASINR performance of the studied configuration, taking the existing LTE network as a reference configuration. So as you can see from figure 2, configuring with different operating bands outperforms all the studied configuration in all percentile. For instance, at 10 percentile, the existing configuration and the configuration with the same operating bands and upgrading with different operating bands provides minus 3.44 dB, minus 5.04 dB, and minus 2.76 dB respectively. And also at 90 percentile, the UASINR performance are 10.12 dB, 8.96 dB, and 11.99 dB respectively. As you can see, in all percentile, upgrading with different operating bands outperforms the other studied scenario. Table 3 shows the aggregate capacity, assuming if all cells are upgraded. For instance, upgrading with 1.8 gigahertz will provide about 48.3% gain, and upgrading with 1.8, of course, with different operating bands, 1.8 and 3.6 gigahertz will provide 144.1%, whereas upgrading with different operating bands, but the with 60 megahertz bandwidth, the 3.6 gigahertz one will provide a 390.93% gains. Again, figure 4 shows, or figure 4 is plotted to show the Pareto frontier of the studied configuration and their corresponding aggregate capacity, considering the existing LTE network as a reference configuration. The aggregate capacity, if all cells are upgraded as an asymptote value, for example, upgrading all the existing network with the same operating bands will provide an aggregate capacity of 1.62 GB, and upgrading with different operating bands will provide about 2.4 gigahertz. Of course, the existing one, the first one is the existing one, the second one is upgrading with the same operating bands, the third one is upgrading with different operating bands, and the last one is upgrading with different operating bands, but 60 megahertz, but the inner one with 60 megahertz bandwidth. Table 4 below shows the performance gain of 28 Pareto locations. For instance, at 10 percentile, upgrading with 1.8 gigahertz will provide 33.1% gain, whereas upgrading with 2.8 and 3.6 gigahertz will provide about 58.6% gains. At 50 percentile, upgrading with 1.8 gigahertz will provide about 39.6%, whereas upgrading with different operating bands will provide about 98.2%. At 90 percentile, upgrading with 1.8 gigahertz will provide 86.3%, whereas at upgrading with 1.8 and 3.6 gigahertz will provide 151.7%. As a conclusion, in future work, in this work, a data-driven antenna planning approach is addressed for optimal placement of full-dimensional MIMO on the top of existing cells. The method provides different Pareto frontiers which can maximize system capacity. Applying this method optimize both cost and capacity. As a future work, static 3D beams in high-rise building and dynamic user-centric 3D beams in 5G mobile network from planning and optimization perspective are an important future work. These are the references that we used. Thank you.